For this video, we're going to take a little bit of a deeper dive into the rational function, which was a parent function that we did look at previously, but we're going to start to explore in more detail today. So a rational function is simply the quotient, which just means it's a fraction, of two polynomials. So it would be something like y equals f of x over g of x, where f of x and g of x are both polynomials and g of x cannot equal 0. So below there are three different examples of rational functions. So if you remember, the rational function, the parent function, was f of x equals 1 over x. This was sometimes also referred to as the reciprocal function. So our general picture looks like this when we graphed it. There were asymptotes on both the x and y axes, and the anchor points were 1, 1, and -1, -1. So let's talk about some of the features. Zeros, remember, are your x-intercepts, and because there is an asymptote on the x-axis, there were no zeros. There was a asymptote on the y-axis as well, so there was no y-intercept. Your vertical and horizontal asymptotes were x equals 0 and y equals 0. Even, odd, or no symmetry. Remember, even is symmetry over the y-axis, odd is symmetry over the origin, and then there's no symmetry. So this had odd symmetry because if you turn your graph upside down, you see the exact same picture. And end behavior. So remember, now we're writing our end behavior in limit notation. So I need the limit as x approaches infinity of y, and the limit as x approaches negative infinity of y. So as I'm approaching positive infinity, that's the right-hand side of my graph, and my graph is going here. Remember that your limit is like your height. So here it's leveling off. The y value is getting closer and closer and closer and closer to 0. As x approaches negative infinity, that's this arrow here. Once again, the limit, your end behavior, is your height, your y value. So it's getting closer and closer and closer and closer to 0 as well. So these are our parent function features for the rational function family of functions. So let's briefly review transformations as well. So if I have a parent function, y equals x squared, or quadratic function, and then I have y equals negative x plus 2 squared minus 4, let's describe these transformations. This negative on the outside is a reflection over the x-axis. This plus 2 on the inside is a horizontal transformation or shift. Remember, the inside is always opposite. So this is moving left 2 units. And then this minus 4 on the outside is a vertical shift down 4 units. So let's apply the same idea to our rational function. So here is my parent function, y equals 1 over x. The easiest one to identify is this plus 3 on the outside. That means I'm going up 3 units. If you want, you can put this x minus 7 in the denominator in parentheses to make it a little bit more obvious, but this minus 7 on the inside is going right 7 units. And then this 2, whatever's in the numerator is like your vertical stretch. So it has a vertical stretch of 2. Because this really could be rewritten as y equals 2 parentheses 1 over x minus 7 plus 3. And it might be easier to see that way as a vertical stretch. So there are my 3 transformations. So let's take a look at example 1. Y equals 1 over x plus 2. So if I'm looking here, this has a horizontal shift 2 units left. So I'm just going to briefly sketch in my original function. My original function, the parent function, looks like this. A little bit more of a curve. But now I'm taking this entire function and I'm moving it left 2 units. So although it didn't move, my asymptote is going to move with me. And that is my new function. So your shift left or right is going to affect your vertical asymptote because my vertical asymptote is now at -2. And it is a vertical line passing through the x-axis, which means it's x equals -2. So that's my vertical asymptote. Your horizontal asymptote did not change. It's still y equals 0, this line here. I still have no x-intercepts. And I do have a y-intercept somewhere around here. We're going to just write C the calculator, but we're not going to worry about that for right now. But it does now have a y-intercept because I shifted over 2 units to the left. So let's take a look at example 2. I have y equals 1 over x plus 3. So now this plus 3 tells me I have a vertical shift up 3 units. So my vertical asymptote is going to stay exactly where it was, x equals 0 on the y-axis. My horizontal asymptote is now going to move up to y equals 3. My anchor points are going to change as well. They're going to be here and here. And there's a sketch of my picture. So my x-intercept is now going to be, see the calculator, and the y-intercept, there's going to be none. Now, to find these where I wrote see the calculator, you could substitute for x equals 0 or y equals 0, depending on what we're looking for, which we'll talk more about tomorrow. You could also use your calculator by finding and using the second trace button and calculating. But right now, we just want to focus on our shifts and our asymptotes. We will formalize all of the rules tomorrow, but hopefully what you've noticed is that your vertical asymptote is you look in the denominator for what makes our function undefined. And your horizontal asymptote, you're going to look at the vertical shift. And as you do more of these, you'll pick up on that pattern. And like I said, we will formalize this tomorrow. All right, let's take a look at example 3. They want us to rewrite our function in the form y equals a over x minus b plus c, and then find our asymptotes. So for this one, it's a little bit straightforward. I want the y by itself, so I have y equals 2 over x minus 4 plus 3. They didn't ask me to, but if they did, a would be 2, b would be negative 4, and c would be 3. So those shortcuts I just talked about are going to help us find our vertical and horizontal asymptotes. So my vertical asymptote, I look in the denominator to see what makes it undefined. So in my denominator, it would be x equals 4 because I have a shift to the right 4 units. My horizontal asymptote, I'm going to look to my vertical shift. So this is y equals 3. If you want right now, you could check these on your calculator as well to take a look. Example 4 wants us to do the same thing, but this time there's nothing to add or subtract, so we have to do some division. I'm going to do a very quick review of synthetic division. We will review long division in a few days as well, so you could do that. But very quickly, my divisor is in the denominator, so that number 4 is the potential 0, which goes on the shelf. And then the 1 and the 3 get lined up. Bring down the 1. 1 times 4 is 4. Add straight down. We get 7. This number is my remainder. So my quotient is 1 plus 7 over, remember your remainder always goes over the divisor. So for us, if I was dividing, it would be in this form, quotient plus remainder over divisor. But for us, we want it in this form here. So I'm just going to reverse it and make it y equals 7 over x minus 4 plus 1. Because now I've identified, they didn't ask me to, but you should be thinking this is up 1, this is a vertical stretch of 7, and this is a shift right 4. So that's why we want it in this form, because it's easier to identify our transformations. And they want us to identify our asymptotes. So my vertical asymptote is going to be x equals 4 because I look to my denominator, and my horizontal asymptote for right now is going to be this piece right here. My function was shifted up 1 unit, so instead of being on the x-axis, it went up 1, which is y equals 1. So there are some examples, of course, for you to try on your own. Once again, if you need to, use your calculator to check your work, because we're still getting familiar with this information. But eventually we'll be doing all of this and even more without our calculators. And we will formalize all of our rules. We'll look more in depth at zeros and things like that in tomorrow's lesson.